Chapter 2 is going to introduce us to some techniques so that we can explore data using tables and using graphs. In the first section of Chapter 2, we're going to look at frequency distributions as a tool for organizing and summarizing data. A frequency distribution is otherwise known as a frequency table, and it gives us our first visual representation of data so that we can start extracting some information about what we see. In a frequency distribution, our data values are typically numerical in nature. So we have values that are numbers, and we put these numbers into different groups or categories called classes. Classes are simply a collection of values. Think of it as a small range of values. These classes have different parts that have their own labels. Each class has a lowest value and a highest value. The lower class limit refers to the smallest number that can belong to a particular class, and an upper class limit is the largest number that can belong to a particular class. Class boundaries are values that fall in between classes, and they are used to make sure that if we have any values that fall in between classes, that we know exactly which of the two surrounding classes to put that value into. So it's a way to make sure that any value knows exactly where it belongs without there being any type of vagueness in the process. Class midpoints are calculated by adding a particular class's lower class limit to its upper class limit and then dividing that sum by 2. So a class midpoint can be thought of as the middle value in a particular class. A class width, on the other hand, refers to the distance between any lower class limit and the next lower class limit. So it requires us to go to two different classes, one that is back to the other, but it is calculated from one class to the next. One of the very common miscalculations that we see is that students will try to find a class width by subtracting a class's lower class limit from its own upper class limit, and so they're only using one class, and that's incorrect. To calculate class width, you have to go from one class to the next, and so it requires two different classes in the calculation. If we were to build a frequency distribution from scratch, which we rarely will have to do in this course, most of the frequency distributions that we'll be working with are ones that have been created for us and that we're trying to evaluate and analyze and extract information from. But if we had to build one from scratch, this is a little algorithm for how to do that. First, you want to decide on how many classes you want. How many groups do you want your values to belong to? Usually that number will be something between 5 and 20, but it could be a little bit more depending on how big your data set is. Next, you'll want to calculate the class width. So how long do you want each class to be? And finally, you're going to calculate your different classes, list them in a table, and then go through your data set and count how many values fall into each one of those categories. This next slide might seem a little confusing before we see an example, but the way to build the frequency distribution is actually going to make a lot more sense once we go through the example, but you can refer back to this slide as we go through that example. Let's take a look at this example, which summarizes the commute time in Los Angeles. So it says, using the daily commute times in Los Angeles from the chapter problem in our book, we're going to follow the procedure that we just saw in the previous two slides to build a frequency distribution. using 7 classes. So this is an example from your textbook. We have 50 different commute times. If you go through that list of 50 values, you see that the smallest of all the values is 5 and the largest is 90. So using the procedure that we saw in the previous 2 slides, we would want to make sure that our first class is going to include that number 5 and that the largest class includes the number 90. Since we're using 7 classes, what we want to do is subtract 5 from 90, which would give us 85. That's the range of our data. 85 then divided by 7 gives us 12.5. And so 12.5 being not such a nice round number, we certainly could use 12.5, but we can go a little bit larger and just use a class width of 15. So you see here below where the data is, we have a table that has one column with the time in minutes for the commute, and in the second column it has the frequency. Now this is the end product. We just want to show you what we're working toward, but we're going to break down step by step how it is that we came across this frequency table. So again, going back to the procedure that we talked about in earlier slides, we were told to use 7 classes. We took the maximum data value of 90 and subtracted from it the minimum value, which was 5, and then we divide that by the total number of desired classes. So that gave us 12.1. Excuse me, I misspoke earlier and said it was 12.5. But nonetheless, we want to round that up to a more convenient number, which in this case 15 works very well. Now we certainly could start the first class with 5, but to make the data look a little bit cleaner, we can set the first lower class limit to 0, which kind of makes sense too, because 0 is a natural starting point for counting time or measuring time. So if we use 0 as the lower class limit for the first class, then to build the second class, we would use 0 plus 15, which would be 15. And then for the third class, the lower class limit would be 15 more than that, so 30. And the next class would go up to 45, and then to 60, etc. So we would be adding 15 each time to get the lower class limits for all of our classes. So the lower class limits would look something like this. Now for the upper class limits, we want to go to whole numbers, and so with the second class starting at 15, we just have to make the first class end at 14. So we want to make sure that all whole numbers are somewhere in either the lower or the upper class limits. And so we have a first class of 0 to 14 minutes, a second class of 15 to 29 minutes, a third class of 30 to 44 minutes, etc. Now, is it possible that some of the data values will fall in between classes? It could. It happens that in this case our data values are all whole numbers. But let's say we actually had a commute time equal to, let's say, 44.3 minutes. That we would determine which of the 2 classes it falls, whether it's the third class or the fourth class, using our class boundaries, which we'll talk about a little bit later. But since we have our classes built, we're going to go ahead and compute the frequencies for each class. Frequency is just a fancy way of saying count or tally. So if we go back to those original 50 values and we count how many of them had values between 0 and 14, we would find that 6 of them did. And then we comb through the list again to find out how many of those values were between 15 and 29, and we would find that there were 18 such values, and so on. That greatest value of 90 we see is the only number between 90 and 104, and so in that last class we had a frequency of just 1. Relative frequencies are pretty easy to calculate. The word relative should remind you that there is a total. So we're looking at counts or frequencies as compared to the total count or the total frequency. So the relative frequency for any class is simply its frequency divided by the sum of all the frequencies. So for example, that very first class that went from 0 to 14 had a frequency of 6. There were a total of 50 times in the table, so the sum of all the frequencies was 50. So the relative frequency for that first class would have been 6 out of 50, which we can reduce to a more simplified fraction. We can convert that to a decimal. So 6 out of 50 would be written as a decimal as 0.12. A percentage for a class also represents relative frequency. It simply is writing that number in percentage form. So for that first class, if the relative frequency was 0.12, written as a percentage, that's 12%. When we are rounding, calculating these percentages, we might introduce a small rounding error, but in theory, all those relative frequencies should have a sum of 100, of course taking into account any small rounding error that could have been introduced. Here's a table that looks very similar to the original frequency distribution. You see that the first column is actually exactly the same with our classes, but in our second column, instead of having the frequencies or the counts, we have relative frequencies. So again, the 12% was calculated because that frequency was 6 for the first class, and the sum of all the frequencies was 50. So 6 out of 50 as a decimal is 0.12, and 0.12 written in percentage form is 12%. When we're able to build a frequency distribution with multiple columns coming from different data sets, we're able to more easily make comparisons. We'll look at an example in the next slide. Whereas in the previous frequency distribution, we were looking at commute times for Los Angeles, this one has commute times in the city of New York and the city of Boise. Notice that we have exactly the first column the same with the different classes, but in the second column we have commute times in New York, and in the third column we have commute times in Boise, Idaho. So if you take a moment to just look at those last two columns, I think that you can start seeing some differences in how those percentages appear. For example, if we look at commute times in the first three classes, from 0 minutes to 44 minutes, so look at the first three rows kind of together, you see that the New York times are kind of low in the beginning, and they start getting a little bit higher percentages as we go down. And with Boise, it's just the opposite. We start pretty high, and then they start kind of tapering off early. And I think that makes sense. Boise, Idaho is a much smaller city than New York, New York, and therefore we would expect that commute times would be lower. New York being a much larger metropolitan city, commute times we would expect to be longer. Now let's look at a cumulative frequency distribution. The word relative in the previous few slides should have reminded you that they are relative to a total, right? Those frequencies can be compared to the total frequencies. So the word relative reminds us that we should make the comparison in terms of the total. Cumulative, on the other hand, that word should remind you of a running tally, a running total. Let's look at the first column here and compare it to the first column of the previous frequency distributions. It does look a little different. Instead of having the first class written as 0 to 14, we write it differently. We say these are values that are less than 15, which is true. For the second class, however, we're no longer just looking at values between 15 and 30. We're looking at all the values that are less than 30, less than the upper class limit. This will include all the values in the first class. When we move to the third class, now we're looking at all the values in the data set that are less than 45. So this would include all of the data values in the original 3 classes. So as we look at the second column, we do see that the first frequency in the cumulative frequency distribution matches the original frequency from the table. After all, there are 6 data values that are less than 15, or in other words, between 0 and 14. However, for the second cumulative frequency, now our number is different. 24 represents the sum of the original frequencies for the first 2 classes combined. So we take the 6 from the first class, we add it to the additional 18 that were values between 15 and 30 for a total of 24 values that are less than 30. So in the cumulative frequency column, you're always going to have numbers that are growing or staying the same. Let's say we absorbed a class that didn't have any counts at all, but we never, ever, ever will go down. So the very last number in the cumulative frequency column should match your total number of values, which in this case is 50, and that's exactly right. We had 50 values total, and all 50 of those values were less than 105. In fact, the highest value was indeed 90. So going from this count here of 49 to the total count of 50 is because we had that last value of 90 in this last class. One type of distribution that is very common in the world in its natural phenomenon is that of a normal distribution. And we're going to spend an entire chapter looking at normal distributions later on in this course. For now, we're going to talk about normal distributions in very, very basic terms. We're going to say that in a normal distribution, the frequencies or the counts start low, then they start to increase until they reach some sort of maximum count or a maximum frequency, and then they start to drop off or become lower at about the same rate that they grew earlier, and so we end up with a distribution that looks somewhat symmetric, or we see some sort of mirroring in the graph. If we take a look at the frequency distribution for those commute times in Los Angeles, we see that the frequency for the first class was quite low, only 2. Then they started to increase to a maximum of about 18. And then lastly, they decreased, and you see that last class had a value of 2. And actually, I don't think this is the Los Angeles one because the numbers are a little different. They may have tweaked the numbers a little bit to show you more of a mirroring. But here's the pattern. Low increases to maximum. From maximum starts decreasing to low again. So there's a good chance that we can call this distribution normal. When we have distributions that have gaps or classes that are empty, that should lead us to ask some questions about what type of influence is present in the data. There's a good example on the next slide. Here we have a frequency distribution that has the weights of pennies, and these are in grams. The first class is going to look at pennies that weigh anywhere from 2.4 grams to 2.49 grams, and so on. So by adding up the frequencies in that second column, we should be able to determine how many pennies were weighed. And it looks like we have 18 plus 19, that's 37. 37 plus 2, that's 39. 39, I'm going to skip over the 25 for now. 39 and 8, that is 47. And then 47 plus 25, it looks like we have, 72 pennies in this distribution. But the interesting thing here is we have very, very high counts of pennies that weigh not so much, between 2.4 grams and about 2.6 grams, and then no pennies at all that weigh anywhere in this middle range, and then we have a high count of penny weights that are in the 3 grams or above. That's an interesting phenomenon, and this would be one where we'd want to investigate why there's a gap in this distribution. Well, there is an explanation. As it turns out, pennies are manufactured a little bit differently now than they were prior to the year 1983. In 1983, there was a change in the composition of the penny percentages in terms of how much of them were made of copper and how much of them consist of zinc. And of course, copper and zinc, being different materials, do have different densities and weights. And so this explains the gap in our data. The pennies that weighed less and the pennies that weighed more quite possibly were manufactured either before 1983 for one group and after 1983 for the other group.